This is a brief introduction to organic chemistry, which deals with carbon compounds. And carbon is a very unusual substance in that it's so versatile it can form thousands and thousands and thousands of different shaped molecules. We get um, many thousands of different kind of molecules can be derived, for example, from a barrel of crude petroleum, which is carbon and hydrogen uh, atoms hooked together, basically, and they can be um, rearranged and so forth to make plastics and pesticides and vitamins and all kinds of things. The key feature of the carbon atom is that it has four sticky spots, or four places in which it can bind. So I'll just draw a carbon atom and put four little sticks sticking out of it. Okay. If you remember looking at the periodic table, we can just take a brief look at that. We see that carbon is right here. Uh, if we count over in the columns, we have column 1, 2, representative column 3, if we skip the transition metals, column 4. So carbon is in representative column 4. Now we know that the column 1 elements tend to give away 1 electron, column 2 elements 2 electrons, representative elements in the third column give away 3 electrons. But carbon is kind of halfway. It's at 4, where compared to the noble gases, which would be at representative column 8. So carbon's kind of 6 of one, half dozen of the other type of thing. So it doesn't know what to do, whether to give away 4 or to take in 4 more electrons. We see that fluorides and other halogens would like to grab 1 electron. Members of the oxygen family would usually like to grab 2 electrons. Nitrogen family would like to grab 3. But what is carbon? Carbon doesn't know what to do. So, but you can kind of see, you can kind of get a feeling for why carbon has 4 bonding sites. But it's certainly not going to be a strong giver of 4 or a strong grabber of 4 electrons. So carbon tends to instead share electrons with other things for the most part. Okay? So carbon's very versatile. Very versatile. Oops. Thousands of different kinds of molecules can be formed. Natural carbon compounds would be, the sugars, starches, proteins, nucleic acids. What else? We have cellulose. And anything in wood. Where else can you? Oh, every body tissues, muscles, things like that. Synthetic carbon compounds would be the various plastics, pesticides, synthetic drugs, vitamins, so forth like that. Okay, so those are just some of the any dyes, different colored dyes and so forth. So these are just some of the natural and synthetic examples of carbon compounds. Okay. Now, I'd like you to learn how to name the basic carbon compounds, and I prepared a little naming sheet here. We can wait till it focuses. And we see that carbon compounds have certain prefixes. that we use. Okay? Such as if the carbon compound only contains one carbon atom, then you would use the prefix meth. Okay? So for example, this right here, CH4, is methane. Okay? Let's look if it has two carbon atoms. Be like, maybe like this, two carbon atoms with some hydrogens hooked on, because remember, each carbon has 4 places it can bond. This has two carbons, single bonded together, so this would be ethane. A 3-carbon chain would be propane. A 4-carbon chain, butane. 5 carbons, pentane. 6 carbons, hexane. 7 carbons, heptane. 8 carbons, octane. Have you ever heard the word octane before, like in gasoline? 9 carbon atoms hooked together, nonane, and then 10 carbon atoms, decane. And above that, you just write the number of carbon atoms, like say C20 or C35. Okay, so if something has, let's say, 1, 2, 3, 4, 5, 6 carbon atoms with hydrogens attached at the various points. I won't draw all the hydrogens in. What would this be called? 1, 2, 3, 4, 5, 6. We go over to 6 carbons. That would be hexane, right? Hexane. Hex referring to 6 carbons. 1, 2, 3, 4, 5, 6 carbons in the chain. Okay, so the prefixes are very useful in learning how to name carbon compounds. Suffixes are also very useful based on the number of bonds between carbons. So if we have this situation here, where we have 3 carbon atoms hooked together by single bonds, then we would say that this is, since it has 3, the prefix would be prop, and then we would use the ane ending, here, propane. So the prefix is prop and the suffix ane, referring to the single bonds between the carbons. Now remember, they also have hydrogens. 1, 2, 3, 4. Remember, 4 bonding sites for each carbon. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so the hydrogens are just kind of secondary there. Let's see if you can try one. What if we have this? And I won't draw the hydrogens in this time. 2, 3, 4. 2, 3, 4. 1, 2, 4. Okay, what would this be called? Well, first of all, it has 1, 2, 3, 4 carbons, so that would be bute. And then we see that there's a double bond here. Since there's a double bond, we use the suffix ene, so this is butene. Now, since there is a possibility that, in other cases that double bond might be somewhere else in this chain besides in the first, we need to use a numbering system. So since this double bond here is right after the number 1 carbon, we'll call this 1-butene. Okay, if we name this 1, 2, 3, 4 carbons, the double bond is right after the first carbon, number 1 carbon, so we call this 1-butene. So that's how that works. So prefixes are useful, and then the suffixes are useful. The prefixes are those 10 prefixes I went over just briefly. You can see them there. You can practice them. And then we have the 3 suffixes, "-ane" for single bonds, "-ine" for double bonds, and "-ine" for triple bonds. Okay? Let's practice drawing something with a triple bond in it. Let's say we have a butine. Uh-oh, there's a triple bond somewhere. Where is it? Well, I don't know, but we have 4 carbons. Let's say we have that triple bond in between the 2 middle carbons this time. So if we name this carbon 1 and 2, 3 and 4, we'd say this would be 2-butine. Now remember, it also has hydrogens hooked on, so I'm going to hook those on right here. Now we have 1, 2, 3, 4. Oh, I don't need any hydrogens there because carbon has already used up all of its bonding sites. 1, 2, 3, 4. And this carbon number 3, 1, 2, 3, 4. So the middle carbons don't really need any hydrogens, do they? In fact, they can't hold any because there's no more room. The carbons have all of their bonding sites used up. So I'll get rid of that little squiggle there. Okay, but then this last carbon, it needs to have 1, 2, 3 hydrogens hooked on like that. Okay? So that's how that works. Now this particular way of drawing a structure is called the full structural formula. Full structural or complete structural formula. There's a little simpler way to draw them. If, for example, you need to type it out on a keyboard or something like that, it's not very easy to type it like this. However, if you use what's called the condensed structural formula, then you can type it out on a keyboard very easily. Look how a condensed structural formula looks. I'll just do it for 2-butine. Okay, this first carbon has 3 hydrogens, so I'll write it as CH3. The second carbon doesn't have any hydrogens, so I'll just put a C there. And the third one doesn't have any either, so I'll just put a C there. And then the fourth one has 3 hydrogens, so I'll put CH3. So this is called the condensed structural formula. There's also something called a line structure or line formula. And let's just take that and make a line formula out of it. There's carbon number 1. I'll just put a little tiny dot. And then the second carbon here, I'll just draw a little diagonal up to the next dot. And then this carbon number 3 here, I'll draw 3 lines there. There's 3 lines. I kind of drew them close together, unfortunately, so that's a triple bond to this carbon. And then to the fourth carbon, just draw it like that. So this is the line structure, and this right here is that triple bond that I kind of made a little, where the lines are a little bit too close together. So this is also a way of writing out 2-butine, the line formula or line structure. So in summary, we have a full structural formula here. We have condensed structural formula here, which is easy to type out. And then the easiest one of all, once you get used to it, that is to draw a line formula, where each end of a segment represents a carbon atom. Here we have a single bond, triple bond, single bond, and the hydrogens are not even included. They're just understood to be there. So line structure um, does not show the hydrogens. Okay? So far so good? Now let's take a look at the idea of how do you deal with a branched chain. A branched chain, I just showed one here. This one has, well, I'll just redraw it. Okay, here we have 1, 2, 3, 4, 5, 6, and then there's one out here. What you need to do if there's a branch chain is look for the longest chain. The longest, and it doesn't have to be in a straight line either. In this case, 1, 2, 3, 4, 5. That's not the longest chain in the straight. Let's go crooked. 1, 2, 3, 4, 5, 6. Now that's the longest chain. So that's called the parent chain. That's the parent chain. And then this is the little offshoot right here. Okay, there's the baby. Little tiny baby. Okay, you always want to name the baby first. Okay, and so now we see that there's only one carbon in the baby chain, if you want to call it that, and there are 6 carbons in the parent chain. So putting these things together, we can name it. Okay, now remember, 1 carbon is a methane, and 6 carbons is hexane. Always name the baby first, put them together. What do you get? We get, well, when you connect these two words, the connector is a YL. That's the connector. So we need to take off, instead of saying methane, hexane, it doesn't sound too good to a chemist, so they'll take that ane off of the first word and write in a YL instead. So this becomes methyl hexane. And what number is the little baby chain or branch? What number carbon is it stuck onto? Well, let's take a look. We count from the side that this is closest to the end, which would be here. So this would be the number 1 carbon, 2 carbon, 3 carbon, 4, 5, and 6. So the little baby chain is on carbon 3, so we would say that this would be 3-methyl hexane. Again, if you have a branched situation like this, don't always count on a straight chain. You need to look for the longest chain, but that's not always in a straight line. Notice how this one is L-shaped. It could even be zigzag shaped. We could have more. All right. The next little section I'd like to talk about would be some of the functional groups. We're not going to go over all of them. We're just going to go over a few. Okay. And you've heard of some of them already, like for example, alcohols. Maybe you've heard of ether. Maybe you've heard of carboxylic acids. Okay, let's take a look. Now, these are based on suffixes. So for example, the suffix for an alcohol, suffixes, the endings in other words, would be OL for alcohol, such as the alcohol in alcoholic beverages, that's ethane, and then you use the ending -ol, right? I'll just underline that for emphasis. So ethanol, right? Maybe we can see what the structure is. Eth refers to how many? It refers to two carbons hooked together, doesn't it? Two. Okay, so that would be two carbons. Ane refers to single bond, and then all refers to the fact that it's an alcohol. Now the functional group for an alcohol, if you look, is that an O and an H, excuse me, let me get the light back on real quick. Okay, the O and the H is hooked onto the carbon chain. That R here stands for carbon chain. So there's an O, an oxygen, and an H hooked onto one of the carbons, like I drew over here. And then we can just fill in with hydrogens anywhere where we need them. So this carbon needs 1, 2, 3, because it has 4 sticky spots. And this carbon needs 1 here and 1 here to make a total of 1, 2, 3, 4 bonding sites. So here's a full structural formula for ethanol. I can draw a condensed structural formula. I'll just put it like this: CH3, CH2, OH. There's a condensed structural formula. If I drew a line formula for that, there's a little dot for the first carbon, here's a dot for the second carbon, and then we just have an OH hooked onto that, like that. Okay? So alcohols they have an O and an H. That's the functional group. That's the alcohol group. I know when we're dealing with inorganic compounds, we like to call this hydroxide, but this is a hydroxyl group or an alcohol group. Let's look at the second type, another type of functional group, and that would be aldehydes. Okay, nasty smelling aldehydes, and the functional group there is a double bonded oxygen hooked on to some end carbon. So if R stands for the carbon chain, on the last carbon you have a double bonded O and an H hooked on. The suffix is Al and pronounced al. So if we have something like ethanal, that Al ending refers to this aldehyde. What would it look like? Well, our value would be two carbons. That's the carbon chain, that R. One carbon in this case. Be one carbon, and then the second carbon is that N carbon, which would contain the double bonded oxygen, and then this. To finish it off, we can just remember that this left-hand carbon has 3 other hydrogens to it. So this is ethanal. Okay? You could do it for propanal, butanal, pentanal, and so forth. Octanal, nonanal, and so on. Okay? This is that functional group called an aldehyde. And the prefix is Al, pronounced al. Another functional group are ketones. Now ketones, don't get confused with the aldehydes. The ketones have their double bonded oxygen in some intermediate carbon within the chain. So you see an R here and an R here. That means that there are carbon chains on each side. So maybe we have something like this. What if we have this? That would be a ketone. The suffix or ending is ONE, pronounced own. Okay, so what would this be? Well, let's look. We have 1, 2, 3, 4, 5 carbons. So that's pent, right? Pent refers to 5 carbons. And there's single bonds between the carbons, so that's ane. And then this has a double bonded O and some intermediate carbon, so that must be it's a ketone, and so the ending would be ONE. So how is this pronounced? Pentanone. Now we need to look at which carbon this is on. Okay, 1, 2, 3, 4, 5. So this is on the third carbon, so this would be 3-pentanone. See how easy that is? Let's look at another functional group, carboxylic acid. Carboxylic acids have a double bonded O and an OH. Don't get confused with the aldehydes. And it's on the N carbon. You can see the R stands for the carbon chain. So what if we have 1, 2, 3 carbons, and that last carbon has a double bonded O and an OH? And the rest of these would have hydrogens. What is this? Well, a 3-carbon chain is prop, right? So this would be prop, single bonds between the carbons, ane. And then how do we name the ending for a carboxylic acid? Oic acid. So this is propanoic acid. That's the ending, the suffix, oic acid. If it's a carboxylic acid, propanoic acid. Okay? The last one that we're going to go over, there are many more, but we're just going to go over these, would be an ether. An ether has an oxygen single bonded between carbon chains. So what if we had something like this? With hydrogens hooked on at the appropriate spots. What would this be? Well, we recognize this is an ether, so the suffix or ending would be ether. This has 1, 2, 3. We can't do it that way, can we? Because it's broken up. So what we have to do is we have to use ether, the word ether, as the ending, and approach it from each side. So here we have, on this side we have F, and on this side we have another F, or 2 carbon, right? So we could say diethane ether, but remember, instead you use the connector YL, so this would be diethyl ether. You don't say diethane ether. Change the ane to YL, and you have a diethyl ether. All right? So those are the different kinds of functional groups. There are other ones too, but I just think that it would be inappropriate at this time to go through that. Okay. So anyway, I'm going to stop at this point before you get too blown out of the water. Thanks a lot, everybody.